This will be a complete review in everything that's in Chapter 15, Benzene and Aromatic Compounds. Before we begin, let's look at a few characteristics of benzene. It has 4 degrees of unsaturation. It's planar with bond angles of 120 degrees. All of the carbons are sp2 hybridized. There are 2 rings of electron density, one above and one below. This means that it can react with strong electrophiles. Because of how stable it is, it doesn't undergo addition reactions like other unsaturated hydrocarbons, but it can undergo substitution if a Lewis acid is present. Its high stability also means it has an unexpectedly low rate of halogenation. Let's look at how we name the different benzene compounds. If it's monosubstituted, you name the substituent and then put the word benzene. Let's look at an example. The compound on the left has an ethyl substituent, so we call this ethylbenzene. This one on the right has a chlorine substituent, so we call this chlorobenzene. Remember to look out for common roots. Here are some of the most common derivatives of benzene. If it is monosubstituted and the substituent is one of these, we call it by its common name. If the ring is disubstituted, we use the prefixes ortho, para, and meta to show the relative position of the substituents. Let's look at an example. There are no common roots, so the names of all of these compounds will end in benzene. On each of these molecules, there are 2 bromines, so these will all be called dibromobenzene. To tell them apart, we use the ortho, meta, and para prefixes. This first one is in the ortho position, so we put an O followed by a dash for ortho. This next one, we put an M and a dash because it's in the meta position, and this last one is in the para position, so we put a P. What do we do if there are common roots? In this one to the left, you can see that there is a toluene. Instead of using benzene at the end, we'll use this. All of the other steps are the same. The substituent's name is bromo and they're in the para position, so we'll name this para-bromotoluene. Let's try another one. Here we have a phenyl group. The substituent is called nitro and it's in the ortho position, so this one is called orth-nitrophenyl. One thing that we didn't have to do for mono or disubstitution is number the substituents. In this example, there are 2 ways you can number. Starting on these substituents, you can go clockwise or counterclockwise to number the other alcohol group. If you go counterclockwise, the alcohol group would be numbered 6. If you go clockwise, the alcohol group would be numbered 2. We want to give the substituents the lowest possible numbers, so the right way would be to go clockwise. Keep in mind that if there is a common root, the substituent has to be given the number 1. Let's try a few examples. Before we start numbering, let's check to see if either of these has a common root. This one on the right has an aniline group, so we'll give the number 1 to this group right here. Let's number the rest of the substituents. Remember that we want to give the lowest possible numbers to each one. Now let's name the substituents. On the left, this one is an ethyl, this one is a propyl, and the last one is chloro. On the right, both substituents are chloro. Next we have to alphabetize them. Even though this chloro has the lowest number, it'll go in front, followed by ethyl, and then propyl. The one on the right has 2 of the same substituents, so we'll use dichloro to name it. We can't use ortho, meta, or para, so we'll have to put the substituent's number to show where it is on the ring. Write the number followed by a dash in front of each name. For the one on the right, we'll write both numbers separated by a comma. Last, we add the suffix. For the one on the left, we'll add benzene to the end. Because the one on the right has a common root, we'll add aniline to the end. Here are the final names. Benzene itself can be a substituent. Here are 2 benzene-based substituents that look very similar. The one on the left is a phenyl group, abbreviated as pH. It has the formula C6H5. The one on the right is a benzyl group. It has an extra CH2 at the end. If a substituent is a type of aromatic ring like benzyl and phenyl, they are called aryl groups. There are 4 criteria a compound must meet to be considered aromatic. It has to be cyclic, planar, completely conjugated, and it must satisfy Huckel's rule. You can use these criteria to determine what kind of compound it is. If it meets all of these criteria, it's aromatic. If it meets all of the criteria but has 4 pi electrons, then it is antiaromatic. If the compound completely lacks one or more of the requirements, it's non-aromatic. Huckel's rule says that an aromatic compound must contain 4 plus 2 pi electrons, n being any integer. You can also just memorize the numbers, 0, 2, 6, 10, 14, and so on. Double bonds and anions give you 2 pi electrons, radicals give you 1, and cations give none at all. Remember that we're counting pi electrons and not atoms. Let's look at a few types of ring-based compounds. Hydrocarbons with a single ring that has alternating double bonds are called anilines. They are easily named by putting the number of pi electrons in brackets, followed by aniline. If there are multiple 6-membered rings with alternating double bonds fused into one compound, you have a PHA. As the number of rings in a compound increases, so does the number of resonance structures. Heterocycles are benzene rings with an oxygen, nitrogen, or sulfur. Let's take a closer look at heterocycles. Heterocycles aren't always aromatic. We have to see if the lone pair disturbs the delocalized system. The molecule on the left is pyridine. I've omitted the double bonds for simplicity. Let's draw the orbitals. All of the carbons are sp2 hybridized, so all of their orbitals will be the same. This nitrogen has an extra lone pair that will be perpendicular to the rest of the p orbitals. It doesn't interfere with the system, and the orbitals here still overlap with the adjacent ones, so this is a conjugated system. That makes this heterocycle aromatic. Ionic compounds can also be aromatic. We use the same method as we just used. If we draw the orbitals on this molecule to the right, we see that this system is still conjugated, making it aromatic. Molecular orbital theory helps explain the bonding in aromatic systems. We have to remember that the number of molecular orbitals is the same as the number of atomic orbitals. If you combine 2 of the same types of orbitals, it is constructive and has lower energy. There will be an increase in electron density between the 2 nuclei. This type of combination is also called bonding orbitals, represented by pi. If you combine opposite phases, it's destructive and has a higher energy. There will be no electron density between the nuclei. This type of bonding is also called antibonding and is represented by pi with an asterisk. There are 6 MOs labeled 1 through 6. Half of them are bonding, while the other half is antibonding. 2 pairs of the molecular orbitals will have the same energy. These are called degenerate. The highest energy orbital is HOMO, while the lowest energy is LUMO. To figure out what orbital is which, first draw your ring with one of the tips facing up. Next, draw a circle around it, making sure that each corner touches the circle. Now, draw a horizontal line through the middle of the ring. The one at the very top is labeled 6, while the one at the very bottom is 1. These 2 that are below the line are one of the degenerate pairs. They have the same energy. Label these as 2 and 3. These 2 above the line are the other degenerate pairs. Label them as 4 and 5. Remember that the 3 vertexes above the line are going to be the antibonding orbitals, so add an asterisk. This method will work for all singular, completely conjugated systems regardless of size. The number of molecular orbitals orbitals is equal to the number of vertices. Congratulations, you have made it to the end of chapter 15.